This is Calculus Lesson 1-2, and this is defining limits and using limit notation. We're going to talk about the formal definition of a limit and talk about how to find limits graphically, analytically, and numerically. The formal definition of a limit is here. I would encourage you to write that down. This was taken directly from the AP Calculus curriculum. It says, given the function f, the limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c from both sides. If the limit exists and is a real number, the notation will be the limit as x approaches c of f of x equals r. Or you could say the limit of f of x as x approaches c is equal to r. That's how you would read that limit notation. So this is the formal definition of what we studied in the first section of calculus when we did basic limits. We said that in order for a function to have a limit, then the y value that the function is approaching from both sides of a specific x value will be your limit of that function at that x value. So we're looking at what's happening from both sides if we're looking at it graphically. Let's look at a limit graphically. When we're doing something with a graph, I'm going to call this function f. And I have a simple graph here. It's got a couple curves. If I had to guess, I would say that's probably a cubic function. You should have learned that in Algebra 2. And if you look at what's happening here, the limit value that I'm going to approach, or the x value that I'm approaching from both sides, is going to be c. If I write out in limit notation what I'm trying to find here, I'm trying to find the limit of f of x as x approaches c for this graph. So I'm trying to figure out what's happening from the left and the right of c. Is it the same? If it is the same from both sides, that would be my limit of the function. So if I look at this function, I see that the limit as x approaches c from the left, it looks like the y value at c would be 1, and from the right, it looks like the y value at c would also be 1. So my limit as x approaches c of f of x here is in fact equal to 1 because it's approaching the same thing from the right and the left. They're coming in or honing in on the same y value there. Now, one thing you have to understand, and we talked about this in the last section, is f of c and the limit as x approaches c can be different. Here, if I want to know what f of c is, well, that's the ordered pair that I get when x is equal to c. Well, f of c here is that solid point 2. So f of c is 2. So it is okay for your limit as x approaches c to be different from the actual f of c value. In this example, I want to find the limit analytically, and sometimes they will give you a function and they'll ask you to find the limit of that function as x approaches a specific value. Well, here they're asking me to find the limit of f of x as x approaches 3. So if I'm going to do this one analytically, I'm going to make a chart of numbers that are very, very, very close or arbitrarily close to the number 3. So if you think about that, I could go, I could put 0, 1, 2, and then numbers bigger than 3, 4, 5, 6, but that might not be close enough to 3 to really tell what the graph is doing. So instead of picking whole numbers, I want to pick numbers that are approaching 3, that are getting very, very, very close to 3. So close, in fact, that they're almost 3. So I'm going to pick numbers like 2.9, 2.99, 2.999. As you can see, as I add another 9, I'm getting closer and closer and closer to 3. That's what they mean by arbitrarily close to the number. And then if you see here, what's happening is at 2.9, my answer, or my f of x, is 4.9. At 2.99, I get 4.99. At 2.999, 4.999. So look at what this is doing. What is that number approaching, or what are these numbers approaching? All right, we don't know what's happening at 3. That's what we're trying to find. But I'm going to then pick some numbers arbitrarily close to 3 from the right-hand side. So I'm kind of going in the opposite direction. 3 is very, very close to 3.001. It's a little less close to 3.01, and then even less close to 3.1. So I am approaching 3 from the right-hand side with these numbers. And you see what happens here. At 3.001, I get 5.001, 5.01, 5.1. So what's happening here as these numbers approach 3 from the right, and as these numbers approach 3 from the left, we are getting very, very close to having a limit of 5. In fact, that is what your limit would be at 3, because we can see that the y values are very, very close to 5. And if this pattern continues, eventually we're going to have 4.9999 repeating, right? 4.9 repeating, which essentially is the same thing as 5. Next, we're going to find limits numerically. And if they give me something to find numerically, and this is my go-to method. If I can find it numerically, I want to, because that's the easiest, most efficient method. The problem is it doesn't always work, and I'll show you some examples of that as we go through the chapter. But if you're given the limit of 2x minus 5 as x approaches 3, well, the easiest way to find the limit is not analytically and not graphically, but it's by plugging that 3 in numerically. We're going to substitute 3 in for the x and see what we get. If it's a nice real number, then we're going to keep that as our limit, because that's what's happening from both sides. So if I plug 3 in, 2 times 3 is 6, and 6 minus 5 is equal to 1. That is, in fact, the limit here. For the second one, the limit of 3x minus 2 as x approaches 2, I'm going to plug 2 in. 3 times x, or 3 times 2 is 6, 6 minus 2 is equal to 4. And for the last one, the limit as x approaches 2 for x squared, I'm going to plug 2 in for x, I end up getting 4. So these are examples of real simple basic limit problems that we can solve with simple substitution. So here's another example I want you to try numerically and see what happens. We're looking for the limit of x squared minus 4 over x minus 2 as x approaches 2. Well, it's not going to be real hard to figure out that if I plug 2 in to the top and to the bottom, what's going to happen is I'm going to end up with 4 minus 4 on top, which is 0, and 2 minus 2 on bottom, which is 0. And we learned in the last section that this is the indeterminate form. If we have the indeterminate form, we can't just say the limit doesn't exist. Now, occasionally that will be the answer, but we have to do some more investigation before we can finally determine what our final answer is going to be here. Now, we've talked about several different things that we can do. We have talked about finding the graph for this and solving it graphically. We've talked about doing it analytically by doing a table, and both of those methods would work fine. You would be able to find the answer, but they're not the most efficient method to use. So if you think back to your algebra knowledge, you're going to be able to do this problem a lot easier and not even have to do a graph and not have to do anything analytically by just doing a little bit of factoring and cancellation. So let's talk about that next. If I have the indeterminate form, the first thing I'm going to do before I run to graph it or before I go to a table and try to do it analytically, okay? The first thing I'm going to do is factor and see if I can get anything to cancel out. Because if I can simplify the function that they give me, then my math is going to be a lot easier to do. Okay, so now, and don't go straight to the factoring and trying to cancel things out. Because if you can plug 2 in and get something that's not the indeterminate form, that would be your answer, okay? But since this one gave us the indeterminate form, I have to do a little bit more to get the answer. So what I'm going to do is I'm going to factor the top, and hopefully you noticed from Algebra 2 that, or really from Algebra 1, that is the difference of squares. So if I factor the difference of squares, I would have x plus 2 and x minus 2 on top. And on bottom, I still have the x minus 2. And hopefully you remember from algebra that if we have the same factor on the top and the bottom, we can cancel those out. So the x minus 2 cancels out to a 1, so it's gone. And we're left with x plus 2. So by doing a little bit of algebra here, I'm able to simplify that thing. And so now what I'm really looking for is the limit as x approaches 2 of the function that's left, x plus 2. Well, if I plug 2 in now, if I do direct substitution now, I should be able to get an answer that will work. So my answer here is 4. Now, if I had done an XY chart and maybe used my calculator to figure out some x and y values, and maybe I had used, numbers that approach 2. Maybe I could use 1.9, 1.99, 1.999, and then approaching from the right, 2.001, 2.01, 2.1. If I use my table menu in a graphing calculator and come up with the y values here, I bet if you did that, they would approach 4. And then again, if you looked at this original function and you decided to graph that function using your Algebra 2 skills, what would happen is we would end up with a hole in the graph at 2, but you would see that that graph approaches 4 from the right and the left if you were to graph that. So there's more than one way to do it, but we want to make sure we use the most efficient method, the quickest method, so that we can get our answer as fast as possible. I have 4 examples here that I want you to try on your own and see if you can get the limits. So go ahead and pause the video, see what you get for these, and then we'll compare our answers in a few minutes. Okay, I've got the answers for the first 3 up here. If I just do direct substitution with the -1, 2 times -1 is -2, minus 4 is -6 for the first one. In the second one, if I plug 5 in, do some direct substitution, 5 squared is 25, plus 1 is 26. And then as the limit as x approaches 1 here, if I plug 1 directly in, 1 squared is 1, plus 2 is 3. Over 1 plus 1 is 2, so you end up with 3/2. So there's no reason to think that we all automatically have to have whole numbers or integer answers. We can have, in fact, it's probably more common to have fraction answers in the whole scheme of things. And then in this one, we've got something that can be simplified. And if I plug -3 in, -3 squared is 9, 9 minus 9 is 0, over -3 plus 3 is 0. So we end up with the indeterminate form here, so we have to do some further investigation using some algebra. We could graph it or we could do it analytically, but we know that if we factoring is probably going to be the easiest thing here. X plus 3 times x minus 3, that's a difference of squares problem, and then we've got the x plus 3 on the bottom. We can then cancel the x plus 3's. So now we're looking for the limit as x approaches -3 of x minus 3. And if I do direct substitution now, -3 minus 3 is -6. So we're able to find that one doing a little bit of algebra.